Good morning, y'all. This is Mr. Berman, and welcome to chemistry class. Continuing with our discussion on thermochemistry, we are going to talk about heat and changes of state. So if you'll remember, changes of state are when something goes from a solid to a liquid, or from a liquid to a gas, or vice versa. One thing that's important to understand about this section is that the temperature does not change during a state change. So if you get an ice cube and you hold it in your hand and it starts to melt, it's starting to melt because energy from your hand is going into the ice, but it does not change its temperature. It'll still be at 0 degrees Celsius until all the ice is melted, and then the liquid water could start to raise in temperature. This is because all the energy that's being transferred in is being used to remove the intermolecular bonds. And none of the energy is going into raising the temperature of the substance. So we have variables describing each of these. The energy that goes in to change a solid to a liquid, the energy that it takes to go from a liquid to a solid, all of those have their own little variables, and we're going to talk about each one of them. So the first one is the molar heat of fusion. It's represented by delta H with the subscript FUS, fuse for fusion. And this is the energy required to melt 1 mole of substance. So last week when we were talking about enthalpy and the heat that is either absorbed or released by the chemical reaction, this is similar. It's still an enthalpy, it's still a change in heat, but it's specifically the energy used for melting. So to go from solid to a liquid. It's important to note that each one of these numbers for different substances is going to be different. Just like the specific heat of a substance is unique to that substance, so is the amount of energy that it's going to take to melt it. You can imagine that it's a lot easier to melt ice into water than it is to melt a block of steel into molten steel, than it is to melt a rock into liquid rock. I think they might call that glass, but you get my point. Now, since there is an amount of energy needed to go from solid to liquid, you can imagine that there's a certain amount of energy needed to go from liquid back to solid. So obviously one of these would be an exothermic reaction, the other would be an endothermic reaction. One's releasing energy, whereas the other is absorbing energy. This one, to go from a liquid to a solid, is called the molar heat of solidification. Pretty easy to remember because it has solid in the name. If you're going to a solid, you want to use solidification. It's represented by delta H with the subscript solid. But it's the same thing. It is the energy required for 1 mole of substance to go from a liquid to a solid. So if you were freezing an ice cube, this is how much energy it would take to freeze that ice cube. Now, because these two things are related, right? You are taking the same substance and you're melting it or you're reforming it. So for each substance, these are related, and they will have the same magnitude, they'll have the same number, but they will have different signs. So we can think of them like this. So the molar heat of fusion is going to be equal to the negative molar heat of solidification. This is how they are connected. Now, if you go all the way back and try to remember the states of matter, you'll remember a chart looking somewhat like this. So this is going from solid to liquid and is melting, whereas going from liquid to solid is called freezing. Liquid to gas is evaporation. And gas to liquid is condensation. We can also skip straight up. So going straight from a solid to a gas is called sublimation. And going straight from a gas to a solid is called deposition. While these things do happen, they're a lot more rare. But you can see, if we have melting and then freezing, we have that pair. We have evaporation and condensation, we have that pair. Which means that we're going to have molar heats of whatever for each of those sets. So in the case of going from liquid to gas, we're going to have the molar heat of vaporization. It's going to be represented by delta H with the subscript VAP, vape, vaporization. And that is the amount of heat needed to go from, for 1 mole of substance to go from a liquid to a gas. Going the other way, we're going to have the molar heat of condensation. This one's represented with, you guessed it, delta H, but with the subscript CON, or you can put COND. I've seen it both ways, but condensation. And again, these two are related, so the delta H vape is going to be equal to the negative delta H cond. Okay. So now let's look at multi-step problems. So what I mean by this is we're going to be raising the temperature of a substance. It's going to melt on us. We're going to keep raising the temperature of a substance. It's going to evaporate on us. And we want to look at each step of those problems. The graph of it's going to look like this, right? If this is temperature versus, oh, this isn't temperature. This is temp versus energy, right? It's going to look kind of like this. So down here it's solid, and it's warming up, warming up, warming up. and then it starts to change from a solid to a liquid. Remember, temperature is not going to go up while it's converting from a solid to a liquid. But once everything's liquid again, it starts heating up, heating up, heating up. And again, we hit that level off as it changes from liquid to gas, and so on. So each one of these sections is going to be a step in our multi-step problem. And the basics of it are, we know how to solve these. This is what we did last time. All the slanted lines, that's going to be following the specific heat formula right here. So if we know the substance, we can look up its specific heat, we can find the mass of the substance, and then we can see the temperature change. That will give us the energy needed to raise it up to its melting point. Then, for the change of state ones, we're going to be using a different formula. In this case, we'll need the delta H for that particular substance times the mass times the molar mass divided by the molar mass. Right? So again, remember that the molar heat, the delta H, is in joules per mole of energy. So we need to find the moles of our substance. If our substance is given to us in grams, then we can convert it from grams to moles by dividing it by its molar mass. Right? A little quick example, if we have 5 grams of H2O, we want to know how many moles that is. The molar mass of hydrogen is 1, the molar mass of oxygen is 16. Since we have 2 of those, it's 2 plus 16 gives us the 18 grams per mole. So then we would just divide 5 grams by the 18 grams per mole, which would give us the moles of water. So that's how you do this part if you're given it in grams. If you're given it in moles, you just got to multiply it by the moles. But these are the 2 steps, right? We're either going to be doing this step or we're going to be doing this step. And at the end, we'll add them all up together. So remember, the first part relates to the slanted parts, whereas the second one relates to the horizontal parts of this multi-step process. Also, to be careful, so this second step with the molar heat, you have to change it for each step. So this one is delta H fusion because it's melting, whereas this one here is going to be the delta H vaporization because it is vaporizing. Don't try to use the same one for both. It's not going to be correct. In fact, it takes a lot more energy to vaporize something than it does to melt something. So keep that in mind. And that is changes of state. Thank you.